In this video, we will investigate the current voltage characteristics of a resonant tunneling diode using a numerical finite difference technique. Before we get started, though, we should probably go over the basics of what's happening in this device.
The resonant tunneling diode, or RTD, is based on the quantum mechanical phenomenon described by the wave function in Schrödinger's equation. Succinctly, the wave function describes the energy of the system, where the left-hand side is the total energy of the wave function, and the right-hand side is the sum of the kinetic energy and the potential energy of the wave function. On its own, the wave function does not mean much, but different operators can be applied to it to find out useful information about the matter described by the wave. For example, if you integrate the conjugate of the wave function times itself over an interval of space, you will calculate the probability of finding the particle in that region. Unlike classical mechanics where particles have an exact location, particles described by the wave function only have probabilities of being in different locations.
When the Schrödinger's equation is solved for a free electron, one with no potential barriers, a pure sinusoidal solution is found. Often, to spatially confine an electron, a wave packet is used, where a sinusoid is placed in the Gaussian envelope. This helps give a general idea of where the particle is.
Another important aspect of the electron that must be known is the kinetic energy of the electron. The wavelength is an important parameter in creating a wave packet, and affects the kinetic energy of the electron it represents by the relation here. The sigma used can also be important in setting the energy if the envelope is not large enough to contain a few cycles of the sinusoid. After some trial and error, a sigma of 10 nanometers was found to be sufficient to envelope electrons at the energies desired.
To simulate this device, Schrödinger's time-dependent equation, as was shown earlier, is broken up into its real and imaginary components and approximated with a finite difference technique. The real and imaginary components are staggered in time, so that the real component is calculated at whole steps, and the imaginary component is calculated at half steps. A wave packet of a specified energy is then sent through barriers, and transmission and reflection probabilities are calculated.
An interesting result that is achieved when the wave function is calculated is the idea of electron tunneling. In classical physics, if a particle encounters a potential energy barrier larger than its own kinetic energy, there is no way for it to get across the barrier without additional supplied kinetic energy. Solutions to the wave function show a slightly different story. If the barrier is thin enough, there's a probability that an electron can tunnel through the barrier and end up on the other side of the barrier without needing any additional energy.
Here, the simulation is tested on a small barrier. The incident electron has an energy of 140 millielectron volts, and the barrier has a height of 150 millielectron volts. For a classical particle, this energy would not be enough for it to go over the barrier, and it would reflect completely. As can clearly be seen here, the electron does go through the barrier with some probability, so there is a probability that an electron can be on the opposite side of the barrier. This idea of tunneling is the primary phenomenon exploited by resonant tunneling diodes.
A diode is any device that allows electrical current through it if voltage is applied in one direction, but doesn't allow current when applied in the opposite direction. Normally, this is achieved through a contact of differently doped semiconductors. But similar characteristics can be found by creating a potential energy profile by growing material with varying band gaps. The structure shown here and simulated later is the double barrier structure. When solving Schrödinger's equation between two closely spaced potential barriers, energy levels become quantized. What this means is that only electrons of specific energies are allowed to transmit in these quantum wells. The gray region in the diagrams shown are areas of the opposite sides of the RTD where electrons are, and the orange line in the quantum well shows a quantized energy level. Initially, when a small bias is applied to the junction, which is seen by a downward slope in the potential energy profile, the gray area does not align with the quantized level. As more bias is applied to the junction, the energy levels align and allow current to flow through the device. Most diodes have an exponentially increasing current with increased voltage, but RTDs are unique in that they have a region of negative differential resistance. That is, they have a region on their IV curve where the slope becomes negative and the current decreases with increasing voltage as the quantized energy level becomes misaligned.
In our simulation, we use material properties based on silicon substrate with the barriers created by regions of compound silicon germanium. The barrier heights are 150 millielectron volts. The barrier widths are 75 angstroms, and the width of the quantum well is 50 angstroms. These values are taken from fabricated devices that have realized IV characteristics. For comparison, the wave packet is created as a 150 millielectron volt electron in a Gaussian envelope. Finally, the reflectance is calculated by dynamically evaluating the integral of the probability density function, as defined earlier, over the space up until the first barrier. The transmittance and in-wall percentages are calculated similarly. As can be seen here, at zero bias, the reflectance is much greater than the transmittance, and very little of the wave packet goes through. The amount of the wave packet that remains in the well is minimal, but suggests that the structure has a role in impeding transmission of the electron. The result would be a relatively low current across the diode when there is no applied voltage.
Of course, the key characteristic of a resonant tunneling diode is that, under appropriate bias voltage, the transmission of current is achievable. In this simulation, we take the same wave packet from before, except this time the potential field has a bias of 0.2 volts across the diode. In effect, as can be seen by the blue outline, the barrier to passage is lowered. This is in turn reflected by the calculated transmission and reflection coefficients, which show much higher transmission than at zero bias.
Simulations so far have been for a single electron at a single energy, but in reality, semiconductors have many electrons at many energies. To calculate the total current through the device, one must know the number of electrons per unit volume, N, the charge per electron, Q, the cross-section area of the diode, A, the distance that each packet travels, delta x, and the time it takes to go that distance, delta t.
Most of the parameters in the previous equation are constants, but the transmitted electrons depends on a couple of relationships. The first is the density of states, which gives the number of occupiable states for electrons per unit energy. The second is the Fermi-Dirac distribution, which gives the number of electrons at a given energy at a specific temperature. When these two functions are multiplied together at a specific energy and temperature, the number of electrons per unit volume per unit energy can be found.
This equation can then be integrated between two energies to find the number of electrons per unit energy between those energies. This integration is approximated in the simulation by multiplying by a small change in energy. The number of total electrons per unit volume in the semiconductor can then be approximated by summing these to infinite energy, or, in the case of the simulation, a sufficiently large energy. The total transmitted electrons can then be found by weighing each term in the summation by the transmission probability of the wave packet at that energy for a given voltage. To finally find current, this term can be input into the main equation for current.
The current is then calculated at various voltages to generate an IV curve. Unfortunately, the simulated results did not match well to the expected curve, with no evidence of a negative differential resistance. This could be due to the weighting of the transmission parameters that was used to account for the density of states in the Fermi-Dirac distribution. The more likely cause of the error is due to the discretization scheme that was used to simulate the equation. Upon inspection of transmission as a function of energy, it was noted that no resonant condition was simulated such that the electron transmitted through a quantized level in the quantum well. Although further study is needed to simulate true resonance in an RTD, the simulation foundation given here is a good starting point for numerical simulations of Schrödinger's equation.